Hello students, we have already studied two postulates of quantum mechanics. In this class we will study the remaining three postulates of quantum mechanics. Okay, for first two postulates we have already discussed. The first postulate says that for every system, each particle will be definitely defined by function called wave function, and there are certain characteristics of properties of a wave function, as we have already discussed in postulate number 1. Then postulate number 2 says that it is the operator postulate, which is that for every observable in classical mechanics there will be a quantum mechanical operator, linear and Hermitian operator in quantum mechanics. So these two postulates we have already seen. Now we will see the postulate number 3, which is known as eigenvalue postulate. Postulate number 3, that is eigenvalue postulate. This postulate says that in any measurement of the observable associated with an operator A, the only values that will be observed are the eigenvalues which satisfy the eigenvalue equation. That is, if any observable property is acted upon by an operator A cap, then the only values that are obtained will be eigenvalue. And it will be according to this equation: A cap of psi is equal to small a into psi. This equation is known as the eigenvalue equation. Okay, according to this equation, psi is a function which represents a property of a system. If it is acted upon by another system, the only value obtained is small a, which is known as eigenvalue. Okay, so this is the postulate. Now we will see what is an eigenvalue or what is an eigenfunction. We will see in the next slide. That is, if a function acted upon by an operator gives the same function multiplied by a constant, then such a function is known as an eigenfunction. For example, if we take this equation, this is the function psi which is acted upon by an operator A cap, and we are getting the product as the same function psi is obtained, which is multiplied by a constant. So when an operator is acted upon a function, we got the same function multiplied by a constant. If such condition is satisfied, then we can call this function as an eigenfunction. So we here psi is an eigenfunction because when an operator A cap is acted upon psi, we are getting the same function multiplied by a constant, or in other words we can say we will be getting a multiple of the same function. Then such functions psi are known as eigenfunctions. Okay, then what is that constant? So when A cap is acted upon psi, we are getting psi multiplied by a constant small a, and this constant by which the function is multiplied is known as eigenvalue. These are known as eigenvalue. So now I think it's clear what we mean by an eigenfunction and eigenvalue. Okay, so in this equation, the function psi is an eigenfunction. It obeys the eigenvalue equation. A cap psi is equal to small a psi, and a is called the eigenvalue. This is the third postulate. So we can check whether a given function is an eigenfunction or not. If we operate that function with an operator, if we are getting the same function multiplied by a constant, then we can call it as an eigenfunction. Okay. Then next we come to postulate number 4, which is called expectation value postulate. expectation value postulate. This postulate says that if a system is in a state described by a normalized wave function psi, then the average value of the observable corresponding to operator A is given by this particular equation. That is, for a system, we know that a particular observable can have values, different values, can have differing values, but the correct value is obtained, is calculated as is the average value of all these observable values, and this average value is known as expectation value, and this expectation value is represented as integral minus infinity to plus infinity psi star a cap psi d tau. So this system is the whole system. We are considering a system which is described by a wave function psi. Then the average value of any observable property can be obtained by this equation by taking the average of that observable values, and this average can be calculated using this equation, and this is called expectation value equation, and this particular postulate is known as expectation value postulate. So for every system, each observable property can be expressed by an expectation value according to this particular equation. So all the properties which are having different values can be expressed by the average of these all values, which is known as the expectation value. So all this postulate is known as expectation value postulate. Okay, now we come to the last postulate. This postulate is known as postulate of time dependent Schrodinger wave equation. So here the postulate says that the wave function that represents the state of a system, the wave function that represents the state of a system changes with time according to the time dependent Schrodinger wave equation, which is given as this. We have already seen that wave function depends on position coordinates and time. Okay, so here this postulate says that the wave function will change according to time, and the variation of this wave function with time is given by the time dependent Schrodinger wave equation, that which is given as h cap psi is equal to I h cross dou psi by dou t, where psi is the function. And this shows the time dependent Schrodinger wave equation. Here we can see that psi is depending on time t, and we know that h cap is the Hamiltonian. But when we take the Hamiltonian, it gives the total energy of a system, which is the sum of the potential energy and kinetic energy. But we can say that potential energy is independent of time. Therefore, Hamiltonian is independent of time. Although the psi is depending on time, Hamiltonian is independent of time. Therefore, we can say that the Schrodinger wave equation, which represents the system, can be split into two parts. One is time dependent Schrodinger equation, and the other one is time independent Schrodinger wave equation. So this is what is known as postulate 5 of the Schrodinger wave equation, time independent Schrodinger wave equation. So this is the fifth postulate, time dependent Schrodinger wave equation. So by this we have completed the 5 different postulates. We will see it one by one. Postulates of quantum mechanics. The first postulate is wave function postulate, which says that the state of a quantum mechanical system is completely specified by a function psi that depends on coordinates of the particle and time, and this function is called a wave function or state function. That is the first postulate. Then continue in this postulate, we have studied about the characteristics of wave function and what are the conditions that has to be satisfied for being an acceptable wave function. Then we are coming to the second postulate, which is known as the operator postulate, which says that for every observable in classical mechanics, there is a linear Hermitian operator in quantum mechanics. So we have studied the definition of operator, and we have gone through the different types of operator used in quantum mechanics, and we have seen what do you mean by a linear operator. We have already seen what do you mean by a Hermitian operator. Then we are coming to algebraic operator, that we will deal it as a separate class, algebraic operator. These are different types of operator. Then we come to the third postulate, that is eigenvalue postulate. It says that in any measurement of the observable associated with operator A, the only values that will be observed are eigenvalues which satisfy the eigenvalue equation. Then we have seen what do you mean by an eigenvalue, what do you mean by an eigenfunction. Okay. Then we come to the first postulate number 4, expectation value postulate, which says that for every we can express all the observables as an average value, and this average value is given known as expectation value, which can be expressed as the according to this equation. Then fifth postulate is time dependent Schrodinger equation, which says that wave function depends on time, therefore it changes with time, whereas the Hamiltonian is time independent. Therefore we can transform the Schrodinger wave equation into two parts, that is, one is time dependent and the other one is time independent Schrodinger wave equation. So we will be dealing with the time dependent and time independent Schrodinger equation in the next class. Okay, so students, we will be meet in the next class. Thank you.